Hello! Updating software is important. Updates are needed to introduce new features, fix security issues, and to adjust to changing environments. Recent trends like agile methods and DevOps further accelerate the speed of updates. For example, high-performing DevOps organizations often update their software in production up to multiple times a day. Not only, but especially at this high pace, it is important that updates don't interrupt the service or even break it. Change is the only constant. We need dynamic updates for workflows. I am Daniel Sokolowski, and this is joint work with Pascal Weisenburger and Guido Salvaneschi at the University of St. Gallen. Plenty of other work has been done on software updates. Work on dynamic code replacement cares about updating a system's code dynamically during execution. Software reconfiguration is about describing and performing changes at runtime. Continuous delivery cares about automating the update process. And even more practical, modern update practices like blue-green and canary deployments implement seamless change. Our work is about safe dynamic software updating, short SafeDSU. SafeDSU is about when it is safe to update a component in a distributed system without breaking a distributed transaction. In contrast to dynamic code replacement, we update entire components, not only parts of their code. Also, we don't look further into the update process itself. However, in contrast to continuous delivery and modern update practices, we don't treat the entire system as a black box. Instead, we closely look at the running transactions and their specification in order to ensure we do not break their execution. Not breaking running transactions is especially important in applications where transactions are frequently executed or take long. Breaking frequently executed and long-running transactions and having to re-execute all of them requires a lot of additional resources and delays their completion too much. Such transactions are often called workflows. They are around since long, for example to describe business processes. But workflows recently gained new popularity in the orchestration of serverless functions. AWS Step Functions, Apache Airflow, or Google Cloud Workflows are just modern platforms to orchestrate and execute workflows. In our work, we enable SafeDSU for workflows. Previous work on SafeDSU solely focused on a synchronous transaction model and had to be applied to an asynchronous execution model for workflows. Moreover, we propose Essential Safety, a new, more efficient SafeDSU approach which we thoroughly compared to previous approaches. Lastly, we evaluated the SafeDSU approaches on 106 realistic collaborative workflows and 8 monorepos. Before we look into an example workflow, let's have a quick look at the typical execution setup for workflows on distributed systems. Each execution of a workflow is called a workflow instance. A workflow instance is executed in a single workflow engine. This workflow engine is the central and only point that knows the workflow instance's definition and state. The workflow engine invokes tasks on components as defined in its workflow instances. In practice, a component could be a microservice or serverless function. A task invocation could be a REST call or a function invocation. When a component executed a task, it sends the result back to the workflow engine, which updates the workflow instance's state and triggers the next task. Of course, the workflow engine may execute many isolated workflow instances at the same time. Moreover, other workflow engines may exist, each managing an own set of workflow instances. However, workflow instances on different workflow engines may use the same components. Let's have a close look at our example, the trip booking workflow. Every box here is a task. The diamonds are gateways where paths split or merge. For each workflow instance, a token is processed from the start node to one of the end nodes. For example, in the successful case, first a hotel is booked, then a car, and then a flight. Another workflow instance could be that a hotel is booked, then a car is booking fails, and then the car and the hotel are cancelled again. We are talking about a distributed system because the tasks of our example workflow are distributed over two components. We call them holiday and car rental, indicated by the swim lanes. It is obvious here that the transaction model of workflows is asynchronous and flat. After a task completes, one or more successors are started. However, previous work solely focused on a synchronous, nested transaction model. Let me show you the difference with the successful execution path of the trip booking workflow. This is an UML sequence diagram using a synchronous transaction model. It is incorrect and different from the workflow's definition. In contrast to what you see here, the holiday component should not be active when the car rental component is, and vice versa. Therefore, the first contribution of our paper is to map the previous approaches to the asynchronous workflow model. This is the same transaction in our asynchronous execution model. We will use it in the remainder of the talk. We are now set for Safe DSU. Safe DSU approaches define an update condition. While the update condition is met, it is safe to update the component. The first safe DSU approach is quiescence. Here it is safe to update a component when it is quiescent. This is the case when the component is not active and will not be active. This means the component does not process a task at the moment and it will not process a task in the future. When we only consider a single workflow instance, you can see here highlighted in blue when the holiday component can be updated, and in red when it is safe to update the car rental component. If we consider multiple workflow instances, the update of a component is only safe if all workflow instances tokens are within these intervals. For instance, now the car rental component can be updated, and now it would not be safe. Quiescence is pretty simple to detect. However, it is overly restrictive. Actually, we can also update a component safely before it is used for the first time in a workflow instance. This leads to version consistency. Version consistency's update condition freeness is less restrictive. It ensures that within a single workflow instance, the same version of a component is used. It is safe to update a component if it is not active, and it will not be active again in a workflow instance in which it already executed a task. Freeness provides the same update intervals as quiescence, and these additional safe update intervals. Having more safe update intervals is what we want. The more safe update intervals there are, the more probable it is to reach a safe update interval quickly when we want to update. So the update timeliness is better. Also, we might have a system that disrupts workflow instances to reach and uphold the update condition. In this case, more safe intervals means less disruption of the workflow instances. One approach that aims to have more safe update intervals than version consistency is tranquility. Tranquility only enforces version consistency between the execution of tasks that run as the successors of the same component. This is more permissive, but is only safe if a black box assumption can be applied. This assumption states that components do not need to ensure consistency within the components they use. Ergo, components may treat the components they use as a black box. However, while such applications might exist, we argue that especially in workflows, this assumption is not generally applicable. Workflows have a holistic, coordinated nature. The black box assumption does often not hold here, while tranquility breaks update safety. We therefore took a step back to version consistency. We wondered, how can we make version consistency more permissive while retaining general update safety? We noticed that not every update has the same impact. In fact, there are many updates that do not change anything meaningful. This means, for some updates, there is semantically no difference between the new and the old version of the component. Kavikov and Robillard also noticed this in their work on version histories, and like them, we call such updates non-essential changes. They stated that non-essential changes are of cosmetic nature, behavior preserving, and are unlikely to provide further insights into the relationships of entities in the component. Easy to detect examples of non-essential changes are updates that only rename variables or change comments and formatting. We use the distinction of non-essential changes and essential changes for our update approach, essential safety. For essential changes, the update condition of essential safety is freeness. But for non-essential changes, we do not apply the and will not be active part of the condition. This results in essential freeness. For non-essential changes, a component can be updated when it is not active. For essential changes, additionally, the component may not be active again in the workflow instance in which it already participated. This results in the safe update intervals shown here. For non-essential changes, essential safety enables these lighter colored additional safe update intervals. In comparison, essential safety enables for non-essential changes the most safe update intervals from all approaches, even more than tranquility. For essential changes, our approach offers the same safe update intervals as version consistency, which is the best generally safe previous approach. Let's now have a close look at safe DSU for a single component over time. Workflow engines run workflow instances which invoke tasks on the component. The invocations are indicated by the colored circles. The component executes the task and returns the results after their completion. With the discussed update conditions, we can determine whether updating the component is safe at a certain point in time. For example, these would be the safe update intervals for essential freeness if the update is a non-essential change. It is safe to update the component when it is not active. However, updates are not instant. Instead, they may require some time to complete. If we start the update in a safe update interval, the safe update interval must be upheld until the update ended. This can trivially be achieved by delaying the start of new task invocations until the component update is completed. Another important aspect is to reach a safe update interval if the update is triggered while updating is not safe. The pink circle is the update trigger. With the waiting strategy that is shown here, we just wait with the update until the next safe update interval starts. However, just waiting can be problematic if the tasks run long and are frequently invoked. Here, waiting is not practical. It can take too long and there is not even a guarantee that a safe update interval is ever reached. Like here, where no safe update interval occurs. Blocking instances solves this issue. Here, task invocations from workflow instances that did not execute a task on the component yet are delayed until after the update. While blocking instances delays new workflow instances, it guarantees that a safe update interval will be reached, assuming that all workflow instances terminate in bounded time. Another alternative is blocking tasks. It blocks all new task invocations instead of only blocking the ones from new workflow instances. Blocking tasks shares all properties with blocking instances, but may reach a safe update interval faster. However, blocking tasks may lead to deadlocks, depending on the update condition and workflows. A last and preferable alternative is concurrent versions. Here, the new software version is immediately started and serves new workflow instances. Already running workflow instances are still served by the old version. The old version is terminated after no workflow instance needs it anymore. It can be used if the old and the new version of the component can safely be operated in parallel. Concurrent versions doesn't interrupt any workflow instance and the new version is active without further delay. However, especially for stateful components, it may be impossible to operate the old and the new version in parallel. In that case, unfortunately, concurrent versions cannot be applied. After having looked at how safe update intervals can conceptually be upheld and reached, we now take a look at how to implement these concepts for workflows on distributed systems. This is again the common setup from the beginning of this talk. When a component shall be updated, we want that it can determine locally whether it meets the update condition. For this, the component needs information about all workflow instances that use it. Moreover, to uphold and reach the update condition, the component must be able to delay the start of tasks or entire workflow instances. In the paper, we propose a modular distributed dissemination algorithm to implement this. Our dissemination algorithm is executed separately for each workflow instance in its workflow engine. The algorithm reacts to events in the execution of the workflow instance and sends information about it to the components. This information is confirmed synchronously by the component before the execution of the workflow instance continues. The components can delay the confirmation, which effectively blocks the workflow instance. The revocation of information is asynchronous without confirmation of the component. A detailed overview about which information is needed for which update approach and reaching strategy is provided in the paper. Our dissemination algorithm enables safe DSU in big distributed systems with many workflow instances and components. Neither workflow engines nor components have to coordinate amongst each other. We only require communication between the entities that anyways communicate. The workflow engines provide information to the components their workflow instances use. In the evaluation of our work, we first wanted to find out whether safe dynamic software updating can be adopted in real-world collaborative workflow applications. Unfortunately, no standard benchmarks exist, possibly due to the complexity and business relevance of our real-world workflows. We therefore constructed a new evaluation dataset based on Repository. Repository is an open online database of realistic BPMN workflows. We selected all collaborative workflows, which means all workflows where the tasks are assigned to participants and more than one participant is involved. We treat each participant as a separate component. Due to various reasons, 57 of these workflows were not executable, but we could recover 28 of them with minimal changes. In total, we obtained an evaluation dataset of 106 executable workflows. As the workflows themselves do not describe the internal behavior of the components, we implemented a discrete event simulation. It simulates the behavior of the BPMN workflows and the component updates. Self-speaking, our simulation implements our dissemination algorithm and supports all discussed updating approaches and strategies to reach and uphold their update conditions. We successfully simulated all workflows in the evaluation dataset, showing that safe DSU can be applied to real-world collaborative workflow applications. With this setup, we also evaluated whether essential safety's overhead is significantly lower compared to the previous approaches. I don't want to go too much into detail here, but generally we found that the impact of safe DSU can be significant. For non-essential changes, essential safety's overhead is negligible, and for essential changes, it is comparable to the state of the art. Seeing the difference for essential and non-essential changes, we wondered about the impact of the share of non-essential changes. We repeated the essential safety experiments with various shares of non-essential changes. As expected, we saw that the higher the share of non-essential changes is, the lower is the impact. If we compare only having non-essential changes with only having essential changes, we measured that there are on average 9.5% more safe update intervals. The time needed for updates and the disruption caused in workflow instances is more than 50% lower. Eventually, we wanted to know how often updates are non-essential changes. To answer this question, we had a look at 8 open source monorepos. It's generally hard to find out which components a commit to a monorepo affects. CI/CD pipelines therefore often redeploy all components for each commit. For each of these updates, we assume that they are essential if a file of the component changed. On average, this was the case for at most 40% of the components. Accordingly, our results suggest that conservatively, at least 60% of the component updates are non-essential. Realistically, the share is even higher. More than 90% of the component updates may be non-essential changes. This was change is the only constant. Dynamic updates for workflows. Safety issue is needed for frequently executed, long-running workflows where breaking workflow instances due to a component update is infeasible. In this work, we applied previous approaches, which were only discussed for synchronous transactions, to asynchronous workflows. We further introduced essential safety as a new safety issue approach. Essential safety leverages the fact that updates do not always introduce semantic changes. For such non-essential changes, a more permissive update condition can be applied while retaining the general update safety. We further gave an overview of strategies to uphold and reach safe update conditions and proposed a dissemination algorithm to implement safety issue in decentralized setups. Our evaluation on 106 realistic collaborative workflows confirms that essential safety effectively reduces the overhead of safety issue. The higher the share of non-essential changes is, the lower is the impact of our safety issue approach. Find out more in our paper. All our data and source code is publicly available and evaluated to be functional and reusable. Check it out and get in touch with us. We would love to discuss with you at virtual or physical XC22 or on any other channel.